Okay, and welcome back to the fundamentals of statistics. We've talked a bit about organizing information into tables and graphs, and both of those related to this really crucial concept of the distributions of scores, how they're organized in terms of how common or uncommon different scores are. So today our focus is going to be on common shapes of the distributions that we'll be working with over the remainder of the semester, some of those key terms that we're going to use and some of the key forms it's going to take. So we've seen those basic tables, we've seen those basic graphs. Again, those all relate to that idea of a distribution, how the numbers are spread out, which scores are more or less common. So here we're going to talk a bit about some of those different shapes. Again, some of the characteristics distributions have. We see a nice little distribution down here at the bottom of the screen. You're going to get real familiar with this one before the course is through. So some of the key terms, when we talk about the peaks of a distribution, we're talking about where the scores are the most frequent, so where that line is the highest. That is at what's called the mode. You may remember that from other math courses in high school or elsewhere, but we're going to learn a bit about that in the next module if not. So those are the most common scores in the data set. When we talk about the tails, we talk about these extremely low and extremely high scores, scores that are really far away from the peak and also have a much, much lower frequency that are very uncommon. So when talking about those peaks, most distributions will be what's called unimodal. They will have only one peak, one clear spot where the scores are the most frequent. The most common unimodal distribution, and the most important one by far, is something called the normal distribution. You may have heard the normal distribution or the normal curve before, or you may have heard it called by its older name, the bell curve. And the normal distribution is the most important type of distribution. We're going to get into a lot of detail on that in a minute. But for now, most important thing, it's unimodal, and this is its picture at the bottom. Some distributions may be bimodal, where they have two distinct peaks. Those peaks don't have to be exactly as high as each other. They don't have to perfectly tie for it to be bimodal, but they have to be pretty close and they have to be distinctly separated. So here we see a distribution with two clear peaks. A variable with really pronounced gender differences might be a bimodal distribution. There are a lot fewer of those than people think, but that might be an example, where, say, women are scoring around here in the right peak and men around here in the left peak, and then there's some overlap. So that again would be bimodal, has two distinct peaks. Either unimodal or bimodal distributions can be symmetrical, where if you split them right down the middle, they would be mirror images of each other. The two halves would look the same. Or you can have an asymmetrical distribution. When a distribution is asymmetrical, its scores tend to pile up towards one end of the range or the other, and you have one kind of long tail, one long series of increasingly low frequency scores in one direction in terms of the range of scores. So it's not perfectly symmetrical. Scores are all bunching up on one side of the distribution or the other. Here's the thing about skew. People use the term skewed in everyday language, but they use it in exactly the opposite way of how statisticians use it. So important thing to keep in mind. Don't blame the statisticians. We came up with it first. It's everybody else that screwed it up. So anyway, when we say things are skewed in a specific direction, what we usually mean is that there's a disproportionate amount of things in that direction. If you said a questionnaire was skewed towards a specific response, like a really high response, you would think there's a lot of really high responses. That's not the way it works. In statistics, the skew is where the scores aren't. So when scores are much less common in the high end of the range, we have what's called a positive skew. Those low frequency scores occur at the higher end of the possible range of scores. When we have the opposite situation, relatively few people have a low score and a lot more people have a high score, it's a negative skew. The skew is where the scores are less common. They're in that extended tail. So positively skewed distributions oftentimes happen when you have a hard floor on a variable, like you can't score below 0, but there's effectively no maximum. Reaction time, for example, tends to show a positive skew, where scores will bunch up in a relatively low range, relatively close to 0, and then you get fewer and fewer and fewer scores far above that. So this is how quickly people recognize numbers after a computer insulted them. It's an interesting study. I'm not familiar with it, but by gosh, I ought to read it. People getting cussed at by computers here. Negatively skewed distributions, on the other hand, oftentimes happen in the opposite situation, where there's a maximum score and most people score pretty close to that maximum score. just think of a really easy test that would be negatively skewed. Most people get near 100%, and relatively few people, again, score much lower than that. Here we see class attendance, another classroom variable, where the most common attendance rate is 100%. Then smaller frequency, we have people that only miss once in a while, lower frequency, people that miss pretty often, people that miss half the time. We see that tail going all the way down to those minimum numbers. So it's a negatively skewed distribution. Next, we're going to talk about the most important distribution shape that, again, a lot of our early tests are going to center around. So a normal distribution is first what's called a theoretical distribution. What this basically means is that it's not a distribution we're making like our previous data sets where we have a bunch of scores and we tally up how common they are. We're not using actual scores. Rather, we're using higher math to determine what an infinite number of scores on the same variable would look like. How does that higher math work? Take a math class. We're not going to talk about it here. We're just going to talk about how it works for us. So again, this is a theoretical distribution. It's not derived from actual scores. A distribution derived from actual scores, by the way, is called an empirical distribution. So the normal curve is the foundation of most common inferential stats, and here's why. It's normal. What they find is just in one of those weird mathematical tendencies, for a great many variables, when you get higher and higher and higher numbers of scores on them, they all start to take the same distribution shape, that normal curve. So remember, the normal curve is normal. It's the most common shape that scores fall into at the population level. That's why it provides kind of a standardized basis for comparing totally different things. So it's unimodal, as we've already mentioned. It's symmetrical. There's uniform variability. What that means is that scores fall off on the left side of the peak in exactly the same way they fall off on the right side. We're going to need more to be continued on that variability, but for now just know that it varies exactly the same for the scores below average as it does for those above it. That's how it's symmetrical. Also important, the farther away you get from the center, the more infrequent scores become, which means they become less and less likely. When we talk about probability, that's going to be an important element there. Scores that are farther in those tails over here are a lot less likely to happen due to chance than scores that are closer to the center, which are much more common. So one of the things that we can do with this, that we're going to learn how to do with this in a couple modules, is because the most variables fall into this exact same pattern and it varies in the exact same way, we can take any specific score, place it on the normal curve, and calculate a percentile. We can figure out what percentage of scores in the population are above or below any given score on that variable. So for any variable that follows a normal distribution, any score we're interested in, we can very precisely calculate what percentage of the entire population is above or below that score without knowing any of those other scores. You just need to know a few basic descriptive statistics. We'll get to that again a few modules down the line, but that's one of the values of this normal distribution. So this is both a point of emphasis and a for future service. It's that important because most variables follow this exact same pattern and it has very specific, consistent characteristics. We can use those characteristics to kind of model the probability of our results. Keep an eye on the normal distribution when it comes up. Make sure that you understand the characteristics that we've talked about here. When it comes back up, pay attention to how we use it. That is a huge, huge, huge part of this process of statistical significance. So to review, again, be familiar with the descriptions of the number of peaks that distributions have, the idea of symmetry. If you are symmetrical, you are unskewed. If you're asymmetrical, you're either going to have a positive or a negative skew, and again, which one is determined by where the scores are uncommon. The normal distribution is unimodal and symmetrical. It's extremely common pattern in large data sets like those populations that we care so much about. It's a crucial concept. Make sure you pay close attention to that, both for this set of material and for where we're heading in the course. All right, that is the end of this section. It's also the end of Module 2. So keep up with your homework and, again, look into those practice problems and their answers. So familiarize yourself with the work. All right, I will see you perhaps in the next module.